The old man will. The old man will. The old man will. The old man builds. The old man builds is broken in the head. People not seeing reality has put them in the red. Where conscious and spirituality been stricken from the norm and replaced with the ignorance of basic magnetic form. The geometry of God keeps running through his head. That's what makes old man builds broken in the head. The old man builds. The old man builds. Spheres of destiny are spinning in his mind, making him travel back and forth in time, battling the establishment for just a little recognition. Has him forcing the world to understand his premonition. That world will have all the technology in the end, even if it means his life will fail to extend. The old man builds. The old man builds. The old man builds. The old man builds.
Hello everyone, my name is Nathan, otherwise known as Old Man Builds, and we have Shawn Calderon here. Shawn,
Hey,
you look great, man. Look
I
at that
appreciate that.
camera.
I appreciate that. Thank you so much, and thank you for having me on.
Shit, dude, not a
Excuse me.
problem. Everybody loves it when you're on.
Thank you. So, is everybody ready to get started?
Oh yeah. We put up a comment real quick, and then
Oh, okay, yeah.
let me add your presentation, Shawn. Go ahead and click it to where you need to. You good?
Yep, I'm good.
You got it then.
All right. Well, thank you, Nathan. Hey, guys in the chat. It's really good to have this opportunity to share what's going on in my lab. I've missed you guys. It was due to health issues because it takes quite a bit to stop me from presenting on these Wednesday evenings. So I appreciate you guys all being here. So this first slide here on top is the frequency that Ian had shared with me from one of his coils. And he asked me, is this the resonant ring that you see in Tesla coils and other resonators? And I said, yes. It's not a perfect resonating resonant ring, but it does have the same kind of flow. And so if I kind of drew out on the bottom here what a more true, a less noisy, more consistent resonant ring looks like. So I thought I'd just share this because if you're seeing this kind of wavelength on your oscilloscopes, then you're probably getting close, or you're nailing the resonant ring of the coil that you are working with. So I thought I'd share that because it could be discouraging sometimes, and look at your waveforms and say, yeah, this doesn't look perfect, but oh, look at Ian's here. Oh, it's not perfect, but it looks like it has this sort of same shape and symmetry and geometry. So a majority of my presentation is going to be on electrets. So here I'm putting on my AC to power this high voltage circuit. And actually, I'm turning everything off, but I'm explaining it as I turn it off. So my setup here is I turn off the power supply and high voltage. And then if you look, I have my melted plastics. You see that there's a plate also on the bottom. What I'm doing is just running voltage from the bottom plate to the top plate. And I create a dense electric field. And then my hope is to cause the molecules in the plastic to move their positives to one side and move all their negatives to the other, and basically polarize them. The more polarized, the stronger the electret. And so you can see here, I'm taking some readings, and we're basically in the middle. 4,000 or 5,000 volts. Higher is probably up to 9,000 volts. Not bad. Measuring the field strength and the voltage of electric fields is very tricky. We'll talk a little bit more about that. But basically, it looks like this is a pass. This did pretty decently. And so I pull these little guys out. I'm trying to do it one-handed so I can hold the camera. And I place them in a little tin foil. And the tin foil just sort of acts like a magnifier. And what it'll do is it'll take the electric fields and sort of bend them back into the plastic. And so it's sort of like keeping the domino effect on the molecules working. And so I've already kick-started the dominoes while I ran the electricity through this green silicone mold here. But now the electric fields are sort of still trying to transform the other molecules that haven't made up their minds yet. And so the tinfoil sort of aids in that. And so that's why I'm always wrapping things in tinfoil. So here's an example of one of the electrets that I made using the process that you saw earlier. If you keep your eye here on that box, there's little lights up here where my arrow is. And basically what you're seeing is when that lights up, then that means that you made an electret that has a decent electric field. Because you saw that there was nothing that lit up, this is a total fail. 99% of what I do with electrets are total failures. I wouldn't say total failures because I do learn from them, but I thought I'd kind of bring you into my lab to kind of see that there's a lot of duds. So here this is basically from the same mold, from the same setup. And look at this. You can see the positive electric field is pretty decent. You're probably going about 9 inches. And so you can see that the red is going to be positive, and all the bars is pretty cool. When I quantify that, it could be in the tens of thousands of volts. So pretty awesome. But you notice that the other one I pulled out had no charge, and this one had charge. Yeah, welcome to the life of trying to control electrostatics. And I'll talk a little bit more about that in a minute. This is the same. I think this is the same one. Yeah. Here we go. So see the blue and then the red. Whenever I get these two kinds of colors, that just means that I'm becoming part of the circuit. Because when we walk around, we can gain charge, and we're sort of walking capacitors. And so the electret was showing one polarity, but that little hints of blue with the red is showing that, I'm sorry, the reverse that, sorry, the little hints of red. The electret is blue negative and I'm red positive. It seems like all of my videos start with this. So, okay, so this is pretty interesting. What I'm doing is when the electret should be positive, it comes out negative. And if the electret's supposed to be negative, it comes out positive. And so there's some interesting physics that's going on. And so this should have come out negative, so it's reading correctly. But the other one that was reading positive, that's not correct. And as we dig into these, we'll talk more. So here, from the same batch, it's positively charged. Every time my hand disappears, I'm flipping it over. So this one's interesting because it's negative on one side and positive on the other. And that's what we call a dipole. And so that's really the end effect that should happen, is that when the molecules are all aligned, then you should have one side of the electret positive and the other side of the electret negative. And this is a win because it's already ahead of the game. Because the other ones are going to still be single charged until they get to that level where they're finally negative, positive, and negative. So if you guys saw, the voltage on this surface was a few thousand volts. Here now I'm wiping it with my secret potion here. And now this working area is 0 volts. Anytime you're working with electrets, you need to 0 volt your environment. You need to 0 volt yourself. You need to 0 volt your meters, and always be cognizant of that, because hidden electric fields will get in the way and drive you nuts. So this one is a little bit easier to do for me. And I found that this is a little more accurate, is putting the electret on top. Now this is an electrostatic meter that actually quantifies the voltage. The max voltage on this meter is 22,000 volts. And so as you saw, I was bringing the electret closer. You can see that it's got a pretty strong field. So if you look at the bars in the upper left, when they're full, you'll see this upper left here again when I do it again here. Let's see. Now the voltage is 1,400 and something volts, but the all the bars here sort of looks like your cell phone bars. When all of those bars are full, that means that you have a more volume of charge, yet you're staying at the same voltage. And that's something that was really tricky to wrap my head around until I started doing a lot of research. And so you can see that as this 1 point something thousand volts happens, then you get all of these bars. That means both volume and voltage are great. If you don't see all those bars, but you see a voltage, what you're seeing is more of a surface charge, not a volume charge. And here I'm going to do it again. See here. So this is one of the funny things is that half of it's charged positive, and the other side is negative, and that has to do with the uneven parameters in the plastic. So if you look at the plastic, it's sort of not flat on top. And that's because that's in the manufacturing process or fabrication process I'm using. So that'll drive you crazy too. If you're just not aware of that, it has uneven surfaces that you're going to get high voltage spots of either polarity. I think I'm showing the same thing here. And so when you saw the voltage that was higher but had less bars, and then the voltage went lower but had more bars, I'd rather have a lower voltage and more bars because that's telling you that there's more charge within the electret. And so, and for me, my parameters for having a successful electret is something that holds a volumetric charge. I think it's called a spatial charge, and that it's able to hold it for a significant period of time. Right, so let's see. Again, this one's uneven surface, so it's sort of all over the place. Sort of the same thing. Give you a little more close up here. Yeah, so I have a dream that the voltage will stay for each side instead of be all over the place, but that's the nature because the charge is just not perfectly even. And there's just a lot of factors. In between these two copper plates, I put in some plastic. And when I start the charge between the plates, I ram the voltage all the way up. And so to make sure that there's voltage inside, I can just tweak it up and then I see this and go, okay. And then I dial it back and I know that there's a strong electric field. Because if there's any doubt, oh my goodness, do I have electric field in here? Is it working? You know, I can't do a measurement inside. Oh, look at that. There's literally quadrillions of fiery, angry electrons causing great fields to occur between those two plates. There's a little bit of a different view. I'm using my pancake fryer. It's another way I check. Just dial it up. Yep, got some plasma. We're going on good. Turn it back to quiet. This power supply I'm using goes up to 100,000 volts, and it's not those cheap Chinese high voltage generators where they say they're 100,000 volts. This is literally a measured, calibrated, tested 100,000 volts. So I'm doing some field strength tests. And I love it when I see that bar light up and I'm far away, because that tells you how far the electric field is reaching, which is pretty cool. So basically it's another about 8, 9, 10 inches. So that has a pretty significant field. So this is a success. And I think some of these are from April. So that's a good thing. They're showing promise. This one surprised me because normally you have to have it in front, but this field is so strong and outreaching that it actually has a sort of perimeter, a spheric perimeter where it's so strong that you can read it from the sides. So I was pretty impressed with this one. That's some good distance. And here's my messy desk. So this is inside my brain. If you want to see it here, it's a disaster. It seems like I'm doing the same thing, but it's this is pretty much what you do when you're building electrets. This is pretty wimpy. I have a whole box of I call it the box of shame, where I have my failed electrets. So I'm always doing a lot of this. Oh, check this out. So you have to be careful because, again, so you see me, it came out of the tinfoil positive. I rubbed it with my finger, it came out negative. Now I'm going to rub it with aluminum again and watch it change polarities. I got, there we go. See, that pesky electron that was hanging out. So just no understanding your environment. It's back to negative again. Understanding how charge is everywhere and charge sort of has a mind of its own. It's a phenomenon that's not really it's complex, I would say. And so I just wanted to show you that as I'm building these, I have to try to always keep myself out of the circuit. And so I'm going to show you how I get myself out of the circuit later. But I thought this one was pretty hilarious. So it's positive. And I'm going to just watch it one more time here. There we go. It's positive. Now I'm going to take away the positive. It's awesome. And now it's negative. So basically what this little electret's doing is it's just surface charges. And so the aluminum is just cleaning up my charge and returning it back to its charge. And so it should be back to positive. We should see red. No, not yet. I love this. There we go. So welcome to inventing and building electrets. Let's see. I just had a bunch of these on my phone, so I thought I would just share everything. So this was a much thicker cylinder that I made. For my setup, it just can't penetrate. It's just not work. It doesn't work for the thicker cylinders that I'm working with. And that's kind of what I'm showing here. This cylinder basically lost its charge after a couple weeks. This meter is awesome. This meter has on the top here, you'll see it has some connectors. You can ground it. It has a positive and negative for you to plug in your multimeter. And so what's cool about it is you're not just going to see lights as the field strength, but you also are going to get a reading on your multimeter. So it's really nice to have a voltage with these bars and the field strengths and densities and all of that good stuff. Now the voltage that you get out onto your multimeter is a little bit strange. So I'm working on an equation, a simple equation, so that way when you plug your meter in, you can use my equation and then it'll give you an exact accurate voltage of each of one of these bars based upon the field strength and polarity of the electret. You're going to tell your friends, hey, I watched the guy put plastic on a meter for an hour. So this is a version 2 set. Look at that, 15,000 volts. I'm getting better at this. I'll tell you what, there's a lot that goes into getting these guys this high. So this is, I'm getting into my level 2. And excuse me, I bought these glass petri dishes. And so I'm going to test. So if you look right here, let's see if I can go back a little bit. If you look right here, I drilled a hole through the glass, and then I put a bunch of solder on the copper plate, and then I put my soldering gun here in this hole in the glass, and it sort of brought some of the solder out. And that way, when I connect this to my high voltage, the electret will be touching between 2 plates. So that's kind of the idea here. And so, yep, we're going to have something in between. That's the plan. So I put some plastic there. I got it warmed up. This is what it looks like when I have the high voltage connected. I have it top and bottom, and there we go. You got a little sandwich here going on. And it's one of my methods, one of my many, many methods. And so I'm not afraid to try different things. It's very therapeutic to put plastics. So here I'm testing it. Hey, do I have plasma in there? Yep, I do. I can see it. Now I'm going to dial it back. One of the things you got to be careful is that there's always a fire hazard with this much voltage, and it sparks something. You guys saw that smoke. And so I have a fire extinguisher next to my workbench just to be safe. And you always want to have 0 plasma, not even a hiss. Has to be quiet. Otherwise, you're going to have an uneven field, and of course, you're going to have that fire danger. See, oh, this is one of my best Electrits level 2. You can see that it's pretty darn far, so the field is drastically stronger because it's reaching out further. So I was pretty proud of this one. My farthest, I think, is 19 inches. And I'll tell you what, that's an amazing find. I hope I don't sound like I'm tooting my own horn, but that's progress, exponential progress from what I'm doing. Here I'm showing off a 19,000 volt negative polarized electret. You can see the uneven edges. I'm going to be working on that process. Here I have this sort of numbering system. I try to wrap these guys in different materials. Here I wrapped it in foam, and all it did was prevent the electret from charging, because if you think of this bubble wrap or this foam here, think of it as a bunch of bubbly electric fields itself. And so those bubbly electric fields in the foam was pushing on the bubbly electric fields in this plastic electric. Therefore, it didn't let the dominoes to fall to get the embers going and start the fire. It actually prevents it. And so it's something I learned. I'm not reading a lot about this. I'm doing this sort of instinctually, kind of like I did my Tesla coils. I just sort of felt my way through and had a blast doing it. Here I'm showing off some higher voltages. So yes, that right there is when that overload looks, it means that it's 22,000 volts or higher. So I'm getting better and better at this electric stuff. And, look at that. So now my guys are going greater than 22,000 volts. So you're seeing the improvement over time. And you can't see the secret codes. I gotta, it's top secret. So here I am. I'm checking my muffins, my plastic muffins. and seeing how they're doing. And here, a cool trick is there's a whole sort of world of home candy making. And if you look at candy making molds, it's nice because now I get to do more experiments at once and then test them and to see what works and doesn't work. So these are silicone. They can take a higher pressure or a higher heat before they melt. And so because of that, it's a great mold to work with. And there we go. It's been in the oven here for undisclosed period of time at an undisclosed voltage. But you can see, look at that. They just need some icing, and we have some really awesome little cupcakes. Now, let's measure one of these little guys. Let's see what their voltage is. It's in the, it wants to hit 20,000 volts. Can we do it? Nope. Now, I've introduced another meter, and all I'm doing is putting the plastic near it, and this aluminum pointer is attracted to it. Now, it's because it's really tough to assess whether you're making progress or not, because every molecule is working against you because they have all of their electric fields, and they don't like it when I'm playing with electric fields and not them. So I have to come up with all these different ways to test them. And this is from an old electroscope that was created in the 19th century, I think. And what happens is when you put the electret near it, let's see here, when you put the electret near it, let's see, sorry, it's got to go. I have more of this. Here we go. When I put the electret near it, what it does is it deforms the electric field, and excuse me, this bar here and the little pointer bar, what happens is they become charged. And when they become charged, they're at the same charge, which means that like charges repel. And so that's why this arrow here wants to get away, because like charges repel. And so that's that movement there. Now it takes a really strong field to move this aluminum pointer. So this is next level power in these electrets. Piece of candy electrets here. I don't know what I'm doing here. Let's see. Again, we're hitting over 22,000 volts. Not bad. Fresh out of the oven. Not bad at all. They start to look like little pieces of candy everywhere. Again, it's really nice to use this method. And this little guy's look at that. It's got a pretty strong field. Pretty strong field for a tiny piece of plastic. This meter is so cool. This meter has so many opportunities. There's so many things you can do with this guy. It really helps you understand the universe around you as it relates to electric fields. Right, so I'm gonna got a scoop of Wheaties here, and I'm gonna put these in these little bowls. So this is sort of what I do in some of my manufacturing process. Here you can see that I'm using salmon eggs here to fill these molds. That's what they look like out of the oven. This is what they look like after they have dried. And so I wanted to sort of, so even though these are little donut candy molds, they're still toroids, and there's just something magical about toroids. So I thought I'd do a little research, and what I found out is this is what the electric fields look like in the torus shape. This is a cross-sectional view, And what I noticed in my research, and this black is what I wrote in, because this is a 3D of the toroid, that there's a null zone here that I found in my research or in my experimentation. So this is something I want to investigate further, and maybe you guys have some cool comments on why it seems like there's a null zone here in the fields. This is yet another shape. These are for making truffles. So I'm telling you what, they do some great things with silicone for molds, and it makes it fun. So here is that cylindrical Electret came out, and it's in the tens of thousands of volts. But later, I found out after my testing that this is only a surface charge, and the aluminum couldn't kickstart the process. So this guy just died. He's in the box of shame right now, but it's worth it testing. And I did some judo top secret stuff to it before. It got to the meter here, and it still didn't help it. It's kind of what my messy bench looks like. And now I used to get excited when the Electrits got over 22,000 volts. There we go. One of my boxes, shame. I think I have a full one too. But now I think it's a good Electret if it can move that big aluminum needle. So that's kind of my second level testing. Here I am playing with talcum powder and glue and all kinds of weird stuff. I'm just going to tell you none of this worked, but it's fun. It's fun. It is a blast. It's fun when you get to this level where you're seeing some progress. Look at all these failures. Once they discolor, you lost. The molecular structure of the polymers are ruined, and so you're not going to get the polarization. Here's my hygrometer, and it tells me the temperature and humidity. Temperature is very important. I'm sorry, humidity is very important. If it's 50 degrees Fahrenheit, or I'm sorry, 50% and higher humidity, then there's a microscopic film of water that coats everything. And so everything is, all your electrets and everything are all gonna look like they failed. So, so in warming up this pancake grill, it drops the humidity within a little bit of vicinity, and that's a good number of humidity right there for to make electrets. And here I am pulling out those booger electrets. They have a super high voltage. I was kind of excited at first, but then I found out it was just a surface charge. So bummer. I'm melting things, pouring things, electrocuting things, uh, filming things. I'm so happy you guys are interested in what I'm doing. I get so excited walking you guys through my experiments in my makeshift lab. So here, I use these little snap connectors to connect these wires. These wires have no insulation on them because they're on a hot surface. So here I am doing my same old charge it from between two plates and warm it up. This is my discharge test. Yeah, smoke is the enemy. I think what's different about this one is that I used glass instead of plastic, and I don't think it worked out. Oh, so this was very interesting. So the material that I was using was creating such a strong field inside that it was pushing up, drawing up parts of the bottom of the plastic because it was warm and pliable, and it started pushing out my secret ooze here. So it's delicate, oh boy, delicate battle to walk that fine line to not get mistakes like this, because the temperature has to be just right. Can't brown the materials. It can't leak the materials, distort the materials, but it needs to be hot enough to where you can put it through electric field and alter its molecular structure. So So yeah, so let's see how this guy looks. All right, so it's, am I going to show the voltage? Yeah, it doesn't even break 1000 volts. So this one doesn't even look right outside the gate. So I'm starting to wire these. I'll hammer these flat with just the nail hammer. That way then when I put the plates together, there's I can put more charge through it before it jumps across and touches each other with the little sparks. And so that's why I do that. This is kind of a cool picture of some of the plastics I'm working in between here. And let's see if there's a better. So there's another, pulling these out of the oven. So just different polymers. I just bought these copper plates on Amazon, and I wanted big, round, thick copper plates, but they were triple the price of these square copper plates. And these square copper plates have the same properties as the round. They're just not sexy like the round. But I wanted the least expensive. Here's what they look like with the infrared. I always do the infrared because I want to know the temperatures, because each polymer has its own temperature. And so I want to try to manage like temperatures with like plastics. And so this is invaluable because if I don't get the right temperatures that I expect, I know I'm already burning them, so I'll just pull them out. So that infrared is invaluable. So this batch is, how did we go here? So again, these are all very different materials. And so this looks like a hit. Looks like a really big hit. This is actually a very strange plastic. I forget what it's called. It'll come to me. And yeah, I think this is a big fail. Yeah. I mean, 1000 volts shouldn't be a big fail, but actually it's a big fail. This is a rubbery. This is more of a rubber. So I have all these little bags of electrets, and I basically run them through a battery of tests. Now that I have the aluminum pointer, whatever fails the aluminum pointer test, I'm going to move them into another bag because I want to keep building on stronger and stronger designs. We're going to cook some more plastic muffins in the oven there. There's a close-up picture. Plastics are pretty interesting materials. I get a kind of I get real excited about my plasma coils where it's very artistic. I feel like I'm finding the art in these plastics as well. So this is that alloy I shared with you guys. And this pan is about 350 degrees, and the metal here melts so quickly. So it's a pretty cool alloy. It's called fusible alloy. This is about half bismuth and half, or about 25% lead. Then it has gallium and other metals in it. Pretty interesting stuff. And the nice thing is that once it dries, cools down, it's reusable. And so, and they don't break the bank. They're not that expensive. But what I was using it here for is I wasn't getting a good heat transfer from the pan to the plate. So this liquid metal really did it. This copper plate is floating on this liquid metal because the liquid metal is more dense. It's the lead and the bismuth are very dense and more dense than the copper. So this copper was slipping around until I tapped it and pushed it out. But there's a suction here, but now the heat transfer from the hot plate to the copper plate is great. It's what I needed. You guys are going to be pros by the time I finish this. It's kind of funny, 100 hours, 200 hours, and I give it in a 30-second video. That's okay. The fun part is finding out what works and doesn't work. And there's a lot of anomalous behavior that I'll probably be sharing in future presentations, but I thought this intro would be fun. All right, so different material. It's the color I don't like, unless it's this color when it's in its raw form. This color is not groovy because the brown ones don't have the same structure. It's just a rule of plastics, I guess. So here again, one-handed filming, trying to get it out so I can show you guys my frustration and my filming. I just pulled it out here for this clip. And again, this is a whole new process I used. And look at that. It just blows 22,000 volts out of the water. I don't even have to hardly manipulate it. And so yeah, this is a great batch, even though it has the browning. So if I get rid of that browning, it's literally going to make the difference. So now it's trick or treat. So I'm going to put these candies away and just mark up the bags and we'll test them later. All right, it's had time to cool. There's that metal. So the metal doesn't scorch. It doesn't mix with anything, and so it's just recyclable. And I can put it in my bin, and then if I need to use it for something else, I've got it. So bismuth and lead and all those other metals, it's pretty cool stuff. So I go to the how to make candies on Amazon. I get all these interesting molds. Excuse me. If you'll notice here, as I bring the Electret down, it moves this little aluminum, this little piece of metal foil. And so this is another one of my tests. If it doesn't move this foil, it goes in the bin that didn't move the aluminum pointer. It goes in a different. Now what's interesting has happened here. I'm going to show you guys it again real quick, but watch this little guy move. This is the old school electroscope. So it's distorting and moving that field. I'm sorry, that little piece of metal. And so I sort of drew the field lines here. And what I'm showing you here is this is all one polarity. This is all negative. These are all majority electrons. These electrons are going to have a field that pushes out radially or straight out. But when it hits this metal, it tends to use the metal as kind of like a conductor. So it's drawn to the conductor, and then it goes through this conductor, this piece of metal here. But then the next field line goes through that little piece of copper foil here. Now, because like charges repel each other, once they jump on both sides here, they repel each other. Ooh, you have cooties. I don't want to be near you. And so that creates that gap here. And so all that means is that this little plastic electret's pushing some serious fields in order to distort the position of this movable piece of foil. And it's pretty good stuff. So that's a sign that I'm going forward. Show you what 100,000 volts looks like. It's crazy cool power supply. Though I think I have a better one on order. I ordered from China. Look at that. You know, that's a mean 100,000 DC, 100,000 volts DC. That's some mean stuff. Here I'm because I've tried different power supplies. You'll notice that I have my famous these are resistors in epoxy. And so that probe that you saw is 490 million ohms. And the reason why it's that specific number is because the internal resistance of the meter is 10 mega ohms. And then once you do the math, it becomes 500 mega ohms or half a giga ohms. And what that means is that since it's impedance matched, I can measure the voltage and then just times it by 50. And so whatever reading you're seeing here, I times it by 50, and then that's the accurate voltage. This is connected to my Wimshurst, and this is a pretty nice Wimshurst. And is it Wimshurst or Wimhurst? I forget now. But notice the aluminum needle, it's moving, but it's sort of, you got to turn the wheel for a few times, and it's not moving that quickly. But the Wimshurst here puts out quite an electric field. And so, and also too, while this is moving, it's discharging about a 1/4 inch gap of electricity. And the reason why you can tell it is the gap releases the charge, and the needle falls back. And so this is a way to test how this meter reacts to a known high voltage source. So when I'm putting my electrets in here, how fast are they moving the needle? So you can see that this is building a field harder almost than the Wimshurst. Now, of course, the Wimshurst is better in the long run, but this is a nice way to say how the field is pretty strong. And you might ask why I'm not connecting the Electret to the top of this meter. There's some crack in here that makes it inconsistent. So to not pull my hair out, I put the Electrets in the middle circle here, and it's the same concept. I'm going to test this little lifesaver I made. Times that by 100, it's a dud. All right. It's touching it, which means not too strong, but look at that. It's pulling on it. Not bad, not great, but this is a little dinky torus or toroid. This one's not bad too. And this is sort of one of my ways to categorize them is this is a measure that I track. One thing you're seeing too here is in the early design of these, the the voltage will drop precipitously. So what you're doing is it has this field that's building up in the aluminum, but it's not quite yet ready to stay steady, like permanent. And so what's happening is that instead of it working on polarizing its own molecules, it's doing the effort here. And so it's losing momentum. So you'll see that the charge will drop greatly. This is kind of out of order, but this is one of the high voltage power supplies that I made. And I put a little antenna here in my O-scope probe. And I'm getting that beautiful resonant ring. I thought I'd just share this because this is the ultimate. Put a little piece of wire in your O-scope probe, put it around a couple inches away from any high voltage power supply, and you'll pick up these interesting resonant ring signals. And so I thought I'd just share that. Look at how fast this one is. So this is, again, this is the version 2. It's showing promise. Now you can see the needle moves slower each time, so it's losing its momentum, but that one has some pretty good field strength. When you're comparing these to the Wimshurst, it's amazing. Look at how fast that one is. Yeah, so this one's got a really strong electric field. It's crazy. So this is one of my big wins. So here's a kind of a picture of my feet with the flip-flops. No, sorry. So this is the setup I was telling you about earlier. You could put the Fluke, well, whatever multimeter you have, and plug it in the back of this E-field measure meter, and it'll give you a voltage, equivalent voltage. And now it only will quantify the bars, but it won't give you a specific high voltage reading. It just tells you that wherever you get an extra millibar, it'll tell you sort of how much change that it had between bars. And so the first bar is going to have less strength, and then the next bar more strength and more strength because the electret's coming closer. and you're going to see that representative on the multimeter. And and I'm working on that equation that will be able to then translate this to volts. And I think this is going to be better because you're going to probably be able to measure 100,000 volts here versus my 22,000 volt electrostatic meter. Here I'm showing you that it's not only the bars, but it's also now you get a voltage reading on your meter. So it's one of the great, really cool things about this. It's called the E-field meter. And so if you want to measure the static charge of everything around you, this is a must, I believe. It's a must because this sensor here at the end is really sensitive. And my goal is right now it's high sensitive mode. But I want to be able to get full bars on low sensitive mode. So that's another goal I've set. Does that mean that these electrets are going to get pretty tough, pretty awesome? You can see that all the bars have 2 point something volts, and one bar is 0.0 something volts. So you can kind of get an idea of the scale of the field and how it diminishes or increases quantitatively. Let's see, is this one of the lifesavers? So one of the things I do too is I'll pull out some of the electrets and I will not put tinfoil on them. So one of these has tinfoil, one of them didn't. And so when I tested them, one of them had a stronger field. And of course it was the one that was not, that was in the foil versus the lower field was the one that wasn't in foil. And so that was what I was doing with this test. So basically foil is your friend with electrets. Now this power supply had a very strange waveform. It sort of had this weird, what do they call this? Triangle wave or sawtooth. It had this weird sawtooth. And then as that sawtooth began reaching a certain kind of frequency, boom, it then resonates. So this was a really fascinating one. Sawtooth, boom, it rings. And then it starts again on the left. Sawtooth, waveform, then boom, it hits resonance. So this is a fascinating waveform from one of my high voltage power supplies. There's a little close up. Here's a kind of a middle section of it. Another look at it. Oh, this gives you the frequency. It's 114 kilohertz. So here's one of my high voltage probes that I make for these experiments. And that's a nice number, 666. Let's see what I'm measuring here. So I'm measuring the output of this 5,000 to 30,000 volt power supply. And because it's going through that big probe I made, it's not frying this fluke, this little multimeter. Now, whatever number you're seeing here, you have to times it by 50. And so that's what I'm doing here is, let's see here. These are resistors that I twisted in a helical form, and there's 13 of them, and these equal 490 mega ohms. And within conjunction of the multimeter, then it reaches half a gig, like I explained earlier. And what this big, huge honking probe does is it takes that high voltage and makes it at such a low current that it's almost imperceptible current. So that way then the meter can receive it without frying the components. So this is my version 3 Electrits. And yeah, this is not a cat turd I scraped off my shoe. This is one of my Electrits. And this thing is just zapped full. This little cracker, this little old piece of bread here, I mean, it just is crazy. Almost every time is 22,000 volts. Look at that. It doesn't look like it should do anything. But this is for me, it's a quantum leap into what I'm working on. So I have to at least show one video with plasma, and I think Nathan's going to talk more about this. But if you recall my other plasma discharges, they're very they look like a bouquet of streamers, plasma streamers, and it's not really though. It's not really this fluffy ball of lightning bolts. It's really just one lightning bolt at a time. And so this fascinated me. This is in slow motion. It's my pyramid coil, and I didn't get to share it in last presentation, so or maybe I did. But this kind of shows you in slow motion that it's one lightning bolt at a time. That's it. It's not this full giant bunch of lightning bolts looking plasma. Pretty cool stuff. This is my phone. I do everything with my phone, so I probably could do this better, but I think you guys are getting at the tip. I'm adding the voltage, and you can see it by how yellow and how thick yellow the streamers are. So I'm just cranking it higher and higher. And you can't really get accurate sound in slow-mo, but it's not very loud. I think that's it with this. All right, so we're in my miscellaneous. I'll move quicker, guys. Sorry, I'm going a little long. So this little gadget I picked up at AliExpress from China, all my Dremel tool stuff works on it, and just having a little sander grinder for little stuff, it's invaluable. So it has the buffing sanding pad on this side. This fits in on your desktop, so you don't have to have some fancy equipment. And I was going to grind these copper plate lines, and it's really a cool tool. Like I said, it's only maybe 20 bucks. It's not expensive, but I thought I'd share. These are cool. These are glass drill bits, and I put one in my drill press to drill, and I was able to drill a hole quite nicely. And these are the little things I like to share because I always wonder how people fabricate things, and so I'm kind of showing how I fabricate and the tools that I use. So if you guys want to take a quick look at this, these drill bits are awesome for glass. If you're ever interested in drilling through glass, and they don't break the bank, maybe 20 bucks, maybe less. So I found this little round pan for making little pastry balls. And so I'm going to be using these as plates for some future electrets. So, and they're both heated. So that's going to be very interesting because right now I only have the bottom heat source. So that's up and coming. And here's that probe that I was telling you guys about. So if you want to snapshot these resistors, there's 13 resistors here. So if you don't have epoxy like this, then you can wrap these resistors with Teflon, plumber's Teflon tape, because it doesn't take a lot, maybe two layers of that tape, and it'll work just as fine. I just like playing with epoxy, so that's what I used. And again, that magic number should be 490 mega ohms. I wrote 487 because that was what my meter was showing at the time, but it's close enough. Doesn't have to be perfect. It won't be perfect with these big resistor values. So if you guys are interested in making your own high voltage probes so they don't fry your meter, I'll give you the resistor here in a second. So these are the tools I'm using to measure high voltage. Here are the resistors that I was mentioning. So you need some, let's see here, you need 550 ohm, 50 mega ohms, and you need 4 10 mega ohms, and that should equal 490 mega ohms. and then it's a total of 13 resistors. So these resistors aren't expensive. And if you use these Mauser part numbers, you'll be able to order them and then refer to the sticky note here. And it'll work with almost every multimeter. And so you can now measure up as high as 30,000 volts. And what that means is when your meter reaches its peak of 600 volts, which is most multimeters, you just times it by 50. So if you have 600 volts on your meter using this probe, it's going to equal 30,000 volts. And so just times everything by 50 and you'll be golden. I think this is a close-up because my camera wasn't really showing it clearly. So if you want to get this part number, the Mauser part number is right there. And then this is the other resistor Mauser part number. And that's it. It's pretty cool. 13 resistors and you're now in business. I use it also for my oscilloscope. So this high voltage probe works really well, and it saves you up to hundreds of dollars. So here I am. I'm measuring the surface that I'm going to be working on. This is a really great surface to work on because, as you can see, it's almost no charge. So these cheap Chinese mats that my wife got me for my desks ended up being really high quality, anti-static, 0 volt potential on the mat. So this is great for measuring electrets or testing them. It's perfect. Here's my old mat, and you notice as I slide it around, it's holding thousands of volts in it, which is just pure torture. Look at that, 6,000 volts. If you remember earlier, I wiped it down with my secret sauce and it went down to 0. This is a couple hours later, it's back up into thousands of volts. So if you really want to get into this, you need to have good hygiene, electrostatic hygiene. Make sure that you understand charge because you'll pull your hair out trying to get any accurate measures. Let's see here. My last slide here. I think I'm just showing you how messy my desk is. Oh boy. Yeah, I don't know what this is. Sorry, guys. It's me sitting down to get some coffee. Oh, hey. So more of the moldy bread that I was able to make. And let's see how it works. See how it goes. Bam. That's good news. Look at that. So both sides work, so not too bad. So I'm onto something. This is a new next level. Yeah, this this maxes everything out. This is another big crusty old moldy pancake. Strong field, strong high voltage. This is looking good. Let me take this crunchy. Looks pretty rough. But yeah, it's got some power. Yes, it does. Yeah, see, when they sent this, it got damaged. It should fall back quite easily. All right, and that's it. That is all. I thank you guys for your patience.
Oh, sorry. Oh, God, I got this all wrong. Sorry about that, Shawn. I'm pushing buttons.
No worries. Well, hey, thanks, guys. So what'd you think, Nathan?
Dude, that was awesome, by the way. I did have a couple of questions.
Sure.
You're going for a monopole? Is that correct?
Right now that is a goal, but right now I have to build what makes sense, a dipole, and I'm struggling to build that. And I think it's just a time thing. I think that it's going to take weeks, maybe months, and then I'll start to see a dipole. But right now, so there's two processes. There's the polarization, and then the unipolarization. And what's interesting is that the heteropolarization has the same charge on both sides. And then the homopolarization has two different polarizations. So that doesn't quite make sense, but it's in my reading here. There's minimal information about this. And so I don't know if that answers your question.
No, it does. I mean, most of them came out with one side of the value. That's why I was asking.
Yeah, and they say that's normal. Doesn't feel normal. Um, and the true test will be how strong the field is, and if it's still the same charge on both sides, then it will be a monopole. So I might be on track.
Do you think it shows up on a higher value, and because the other side's weaker, it just doesn't show up, but it still has both poles?
So because there's not a smooth surface, there is cracks and crevices where it's dipole.
Gotcha.
It's
Makes sense.
that's kind of part of it. Good question.
I was asking because William had asked quite a bit of questions about it, in which way it was going.
All right, I'm just gonna check here real quick. Just a little bit. Want to see here who's on. Okay.
How much output does it take to trigger that LED in your little device where you put it up to it?
How much voltage to get
Yes.
1 bar? So it's probably around 700 volts.
Wow.
Yeah,
Okay.
yeah. And it's not completely linear, so it doesn't have this nice smooth ramp. It's more of a bumpy ramp. Each bar it goes higher each bar, but it doesn't follow this slope. It's more of this the next bar is 100 volts difference, and then the next bar is 1,000 volts difference, and it's always climbing.
Gotta love that.
It gives insight into how that there's inconsistencies in my polarization process because it's an uneven surface, so it's going to have uneven charges at distances. Oh, hey, thanks, Joe. Thank you, guys.
So I'll let you read all of them in a second, Shawn. Shawn might want to try measuring the weights of each one. See if there's a correlation between the strength of the field and the weight. That's interesting. The field mass.
And it says a carat scale, which is interesting. Believe it or not, the thinner electrets are stronger and thicker ones aren't. And now you might be able to say, well, of course, thicker is harder to get more electric intensity or electric density, field density into the thicker materials. And so that makes sense. So if I were able to build a significant charge on a thicker material, it would be the stronger electret. So mass is directly proportional to its voltage if I am able to polarize them. But in my experiments, it's always the thinner, lighter that carry the highest voltage. So I don't know if you remember that really thin electret that had some burnt spots on it, and I put it in, and the arrow just flew real quick. That aluminum arrow just flew. That was my thinnest electret, and you saw that. So
I think he's trying to see is if you get a higher electrical value, are you gaining mass?
Oh.
Because we always equivalate energy to mass, and you know what I mean? You get conversion there. So it's just wondering on a different level if it's doing that.
Yeah, and I guess a carat scale is very sensitive. So it might pick up on those that's a really good suggestion. Thank you for the comment. I didn't even think about weighing them. I'm very focused on just polarization right now.
Mhm.
I'm trying to control molecules, make them slaves to my will, and it's
We
yeah.
need to we need to get you some injection molding, so you could set it your setup and then inject it and then let it cool while it's in that field. You know what I mean? That you preset that
Yeah.
way, every one of them comes out the same, and then the whole thing is a capacitor later on. Just my own personal thing. You probably got a plate long enough. You know what I mean? A list long enough on yours.
No, that's a great suggestion. I was looking, so the more you incorporate into the creation, the electric creation process, the faster of the creation and the longer, I'm sorry, and the bigger the fields. So I was looking at how to add pressure to my creation process. And so it seems like injection molding would give me pressure.
Yes.
So thank you for that. Yeah, I'm gonna write it down.
Well, they got it. It'll also equalize the melting so that you don't get burnt. It's an even
Yeah,
flow
yeah.
in a tube. Well, the way they do it anyway. You know what I mean? They keep it in the same heat level. They put it in. There's no burning. Just have to
Mhm.
make sure the heat's right with the surface. You know what I
Right.
mean?
Makes sense. Thank you. Yeah, I'm writing that down. Um, awesome. Yeah, yeah. Eighth
Yeah.
sin
Well,
it says.
it would also, sorry, it would
No,
also
no.
create the same exact thickness in every single one of them, and maybe smooth out the sides on the plates.
Yeah, yeah. Yeah, I've been focused on dirty, quick and dirty, so I can
Get your
because
head
it's
around
so
it. I get
easy.
it.
Yeah, so easy to go wrong. And it's frustrating when you make 100 that don't work.
I'm going to tell you, Shawn, it's easy to sit on the outside over here. I would hate to be you playing with that. You
It's
probably
a,
get zapped half a million times, or I know I would. I don't think there'd be a day go by when you get zapped.
it's right. You're right because it's really a pancake grill when you come to think of it, and yet I'm pumping 20, 30,000 volts through it, and I'll just grab something off of it. It just bites.
Oh,
Now I have the
no,
one-handed rule because that's just safe, but it doesn't mean that one hand doesn't get whacked.
trying to
Yeah.
get the Einstein hairdo. So,
Yeah. Yes, yes.
oh,
All right.
that's funny.
Eighth center says thickness is relative to the size of the particles as it relates to Euler's interscalar geometry.
Mm.
Yeah, interesting. I'm just reading the comments here.
Oh, yeah, go for it.
John Bigman asks, would it be possible to make polarized tubes like glass tubes? I haven't played with polarizing glass yet. That's next level because you're going to need greater temperatures, and glass can be dangerous if you don't know how to work with it.
Mhm.
Um, but glass would be definitely more permanent electret if I was able to polarize glass because glass is a great dielectric, and because of that, it can hold a lot of charge. And what John's saying here is polarizing a glass tube would be fascinating because would you have the null point of the fields inside the tube? Remember I
Oh,
showed you
hmm,
how the lines distort, the field lines of the electric field distort. So yeah, maybe the null point's in that pipe.
that'd be interesting. I agree with you on
Yeah,
that one. Hmm.
taking notes here, guys. Right. Uh oh, Coat, congrats. Oh, thank you, Coat. Lord of Plasma, please don't vaporize me. You're awesome, buddy. Let's see.
Oh,
Daniel Foster says high K factor electrets, bentonite, and Rochelle salt, bismuth, calcium, gold, ceramic, piezoelectric insulators, gradient, weave options available. Yeah, that's some next level stuff. I understand what you're saying exactly. Um, what he's kind of basically saying is that electrets have other properties. In fact, I think I highlighted in my notes here. It has two interesting properties. Reading this paper here. Electrets are pyroelectric and piezoelectric. So I was reading this, pretty interesting. I have to research those, but when I first started researching it, bentonite came up, and so did the ceramic piezo, and yeah. So you're on the right track, Daniel Foster. So thank you. Yeah, I'm basically titanates are also supposed to be really good at holding permanent polarities. So thanks for sharing. Okay, there's a lot of goofy banter in the comments.
that's me.
Oh,
So
too.
I get to play around while you're hard at work.
Oh, thanks. We're a team. Let's see here. All right. It's pronounced Oilers. Yeah, that Euler uh comment. It's something like Oilers.
Hmm.
Let's see. Daniel Foster says acrylic glass electrodes doped with monatomics.
Mm.
Mono
Yeah,
monatomic.
monatomics. Yeah, the
Hmm.
breakdown of metal in a small electrical field. That's
Huh.
what Bernie works on.
Yeah. I remember hearing Bernie mention it, but I'm gonna write that down. It sounds really fascinating. Oh, by the way, too, a huge credit to Brent Jarvis for all of this. He's the Electret expert, and so we meet or talk about these experiments, and he's always a huge help. Gives me great suggestions. So kudos, and his name is also Vortex,
Yep,
or
changed
his
it on
name
us.
is Mr. Lanius. So he has many names. But yeah, him and I are the Electret Siamese twins right now, joined at the hips.
Nice.
So monatomics, I'm gonna write that down. All right. So Dennis Matovich says, oh, he's talking to John Bigman. Sorry.
Hmm. Oh, they were talking about that Tesla coil that I showed you earlier. I'll have to show it by the end of the show.
Yeah.
Remember,
Sure.
Dennis was lighting up a light bulb, and he put the wire around that light bulb, and it changed
Yeah.
colors under the camera being at slow speeds, which is I've never seen that. In every Tesla coil video I've watched, I've never seen that.
Yeah, there's something about the way he's affecting the electromagnetic light. I just the waves, because that's given the different colors.
Well, let's take a look real quick. We'll evaluate it. We'll get back to the questions. Is that okay?
Yeah.
That way he can get your opinion on it.
Yeah. Mystic Coat, you're late.
So he's got the one wire energy wrapped around the
That's
light.
crazy. So, so we know that there's plasma. It's the gas inside the fluorescent tube. Are you hearing the voice? I can't hear it.
No, oh my God. This was, sorry, I'll just show that real quick. It's anti-gravity right there. That has to do with sound.
Oh, interesting. Didgeridoos are awesome.
Sorry, let me go back. It keeps flipping real fast because the video is short.
Mm-hmm. Yeah, so with plasma being inside the light bulb, we know you can move plasma with magnetic waves, magnetism. And so we know also that a conductor, copper wire, creates a magnetic field. And so in creating that high voltage magnetic field, it's compressing, or maybe it's doing something to the electrons in the plasma to emit different colors. And that I would have to think about this one. What are your thoughts?
Well, we always see the test where they put gas in a tube and they magnetically pinch it, and we see it come down, but it doesn't change color. This one is wrapping the wire around. So
Yeah, right.
anytime you take that wire that goes down the center and wrap it, it starts
Yeah,
to create a magnetic field in it. So when you do that to the light bulb, he's got to be affecting the gas inside there. So it's got to be compressing the gas in
yeah,
that one area, causing the change in color.
yeah,
The awesome thing is it's changing color like that. I never seen it. I never
yeah,
wrapped the wire around it, but and Dennis says it's in super slow motion, which, by the way, kudos to you for doing that because
yeah.
that's amazing.
It is amazing. It's now, is that coil on the outside connected to the center rod of the Tesla coil?
Yes,
Okay. I just want to make sure because I'm taking notes here. I would like
we all got to try it, huh?
I want to try it. Yes. I got plenty of Tesla coils to test it with, so just gonna draw a little picture here for me. Yeah, that is crazy.
Let me see if the speed thing on this. Man, it's gonna go off to all kinds of different stuff. I don't know the setting on it. Playback speed. Yeah, 1.5. Or sorry.
Oh, no worries. I'm just reading the comments. Let's see. Howdy, Yanni. Yeah, there's some tangents in the comments.
Yeah, it looks like a cop car blinking lights without the blue.
Doesn't it?
We're all in trouble now. Hey, there's a little different color. Look at that, Shawn.
Yeah, and it's like a violet. It did have a little blue there too. It's just super quick. It is running a spectrum of colors, which
Yeah.
means that there's different wavelengths. And so is the magnetism compressing it to different wavelengths? I mean, that's what it looks like, right?
But okay, let's throw a theory out there. If it's a gas in a compressed field, which in the tube it has to be compressed, right? Now
Mm-hmm.
you're adding extra compression. It's like pushing on the side of a balloon, right? That's
Mm-hmm.
filled with something, and it's causing it to produce more energy in that area.
Mm-hmm.
So, in thinking of it in that aspect, it's
Mm-hmm.
like the sun when it shoots off some plasma or something from it,
Yeah,
and
yeah.
it comes towards the Earth, and you get that effect pushing on our
The
atmosphere right
magnetosphere.
there.
The
There you
magnetosphere.
go, and then the light spectrum changes a little bit because
Oh,
you're pushing
yeah.
on that gas.
Yes. When the solar flare reaches, basically it's aimed at us. And yeah, the magnetosphere, the magnetic protection field around the Earth, yeah, it does compress it. And then it has to go around it. And as it's compressed and going around it, you get those northern lights in
Yeah,
the
there you go.
hemispheres.
We
Uh,
see all the different colors there, right? We usually
yeah,
see green, but yeah.
exactly. The aurora borealis, I think, is another name for it.
Mm.
Yeah, no, that's a really good analogy or a point.
That's so funny. You have to think about everything that's in the earth to get this because you're like, well, there's gas in there, they keep telling us, you know what I mean? And we break down what it is, and then What's the
Yeah,
field on the outside made of? How does it work when you push against it? There's a lot there, man.
there is. There is. I think that's was a great way to explain it. Really helped me understand it. Let's
Yeah,
see.
now we all got to try it. By the way, Shawn, I need to send you one of these coils for testing, so that yeah, you need to test everything on it.
Well, yeah, let me order one.
No, don't order it. I'll send it to you.
Okay, appreciate it.
Yeah.
Code
I
Creative. Sorry, Code is asking, can those tubes make X-rays? All caps, Shawn.
ooh.
um, so that's a good question. I have to imagine that there is some radiation in plasma. I don't think it's a dangerous level with the AC, with the Tesla coil, but the high voltage DC, that's a really good question. That's something worth looking up because I think we might have some low level X-rays in the high voltage DC. Do you remember that wire, Nathan, that was hanging out over the pancake grill? And then I cranked in all these lightning bolts, sorry,
Yes.
came out of the wire. Yeah, that was the full strength, and that was about 3 inches, 2.5 inches from the grill. But that's a DC you don't want to mess with. That's the kind of DC that will fry you. I know AC is more dangerous usually than DC, but this is a DC that you want to watch out for. So is it putting out X-rays? Probably. At dangerous levels, I don't know. I do have a welding shield that has the it's the full face shield, but it's for welding. So it's that dark tint.
Hmm.
I'll use that when I'm doing super high DC light experiments because it's that
No.
really thick white, that
Mhm.
really deep white, and there has to be stuff bad for you. And
No more
so,
suntan for you, huh?
yeah, exactly. A 30-second suntan. Um, and then behind me, there's an X-ray on my wall of my head. You know, it's yeah.
Oh,
Good
by the
question,
way,
Carl.
um, sorry, I just got to mention this. If you look up the patent from Tesla, and it has to do with X-rays and his cold energy X-rays, where he said that they're not as harmful as the X-rays we use today.
Yeah,
Uh, John Brock, I believe his name is,
yeah.
um,
Mhm.
did the tube, and he's trying to use that to show you the X-ray. As a matter of fact, he did show it to you on a CRT TV. He showed you the X-rays with the cold energy.
And he made that coil. He made
Yes.
that CRT. I ordered one from his website a year ago,
Oh,
and
really?
I still don't have it. I
Oh,
don't want a refund because okay, I'm not in a hurry, but I really want that tube he designed. It's an
yeah.
X-ray tube, but it's the safe X-rays.
I'd like to see how he's compressing that field, whether he's sucking the air out or adding the air to it. You know what I mean? Is he adding any kind of mist in there or anything like that? I don't think he does, but
Yeah.
in a lot of this stuff, I found the temperature of it really matters to pull out that blue. If I wanted to get the blue, I could pull a little bit of the air out and drop the temperature of the actual glass, and
Yeah.
then man, I could get that sucker to glow. It's like the glow bug.
Yeah. You know, it's your compression idea is starting to make more sense because red is a bigger wavelength than blue. Blue is a smaller wavelength, so maybe those light changes are compression and what's the word? Compression, decompression.
Mhm.
The back and forth is getting the light. Something's compressing. I totally think that's the right track.
I think so too. I think compression has more to do with all of our coils than we realize.
Yeah.
Everything we do, even if they're wound straight up, there's still compressive value in each layer. When you wind them with multiple turns, but in a sphere, you
Hmm.
have a compressive value. And where that compression takes out is the color of your plasma that comes out of it. So you have the little tip that goes in a little
Mm,
bit, but it
yeah.
comes out purple. And it seems to want to get away from you. And then if you don't do that, it comes out white and it likes to attract itself to you, and you don't like that. So
No. Yeah,
it has to do with
been
that
there.
compression. And I don't think we figured out exactly how much. I'd say there's a long, long way to go in that.
Yeah, I don't think I explained it in my presentation, but when you're placing a charged insulator, an electret, and you put it on a non-conductive surface like a plastic mat,
Mhm.
you're getting fields basically pushing against each other. And I use the analogy of the electret being a basketball, and then you have they're the fun parks. Um, they are the fun places for kids at McDonald's, the McDonald's Play Center, and they'll have that big box of balls. I know because my 4 kids loved them, and they would dive into these balls. Well, I think that the material around us are those balls. Those are the electric fields, because electric fields are 3D. They're not straight one-dimensional things we draw on paper. Um, and then the basketball is the electric. And so they're sort of just fields pushing on each other.
Mhm.
And because the basketball is getting pushed at the bottom, it's getting a little bit of distortion, and the balls under are getting more of a distortion. And I make mention of that because you're right, there are pressures everywhere. Voltage is pressure. So when I
Mhm.
was sliding that electrostatic meter across that plastic surface, it was given different voltages in the thousands.
Mhm.
That speaks to, you're right. That's it's a voltage. A voltage is always pushing or pulling, which is pressure.
Yeah. No, we see it in. I don't think we realize it the right way. We use these light bulbs, right? And we just think they're light bulbs, but really they're compressed gas. And when you start thinking about it, you said, "Well, I just put a radiant field to compress gas." It changes your outlook on what you're doing, because normally you say, "Man, I just put a field out there and it's a Tesla coil field, and I whip my light around, it works great," right? But
Hmm.
when you look into what they're actually doing, I took a compressed gas cylinder with gas inside of it, and now I'm forcing pressure upon it in order to change the color. So based on whatever pressure is putting on there, you might get a whole light spectrum, which is what we just saw.
Yeah, yeah, and translate that pressure maybe into um, energy levels, or what is it called? Uh, Energy levels. It's an excitation um, of when you pressure is applied. It's an excitation of the electrons, and the electrons, depending on their orbit, are going to emit different colors light.
Mm,
Mean, I'm throwing that out there. It seems to make sense. Your pressure idea is, whenever you make it, oh, that's a pump. Oh, that's pressure. That gets me scratching my head initially, and then when I go back to my test bench, like, oh my goodness, he's so right. And so uh, you're more of an effect guy than a cause guy.
oh
You
yeah.
sort of think things, hey, this is what it's already done, and this is the right answer. And then you kind of go, how do we get to that right answer? Um, Whereas most people kind of think at the beginning, and then you just think holistically. You're 360-degree mind, if you will.
Well, I'll tell you this, Shawn. I'm not afraid to say it. I'm like a caveman. Explain it how you see it, and then have a physicist come along and explain it the right way, and then we're all good. You know what I mean? I have no problem with that, because there's a lot of, like you say, electrons. If I can't see it, I can't explain it. If I
Yeah.
can see it, I can explain it. If I can feel the field, I can explain it. But
Hmm.
when I can't see an electron, it makes it hard to distinguish if it's there or not. I see
Right.
a lot of things that have buildups of charge that feel like impedance on things,
Hmm.
and they slow things down. They slow down resonance. To me, that's the electron. It could just be the beginnings of an evo. So I can't distinguish the difference. I'll be very honest with you. But when it comes to fields and seeing each one individually and knowing,
Hmm.
hey, we're in this field, this field, this field, yeah, no problem. But electrons, you got me.
Yeah. I mean, all the sparks out of your Tesla coil are electrons looking for a home, or they're being sucked in. There's this sort of push pull, which you call a pump, which really helped me understand it better. But yeah, those are just dancing electrons on on this uh, the streamer of plasma that you have is in the background. Um, but electrons are they're conceptual. They're a complex concept, and I think that's why you know how to get them to do what you want. You do. You have an intuition about electricity. There's no way you could get this far if you didn't have a gifting. Totally. I know people with high degrees in physics and electrical engineering, and they couldn't touch your designs. They wouldn't even know what it is. It's so advanced. They would it would be like what is it? Oh my goodness, 2001: Space Odyssey, where
Mm,
condensed plasma,
yeah.
where the monkeys all run out. And there's like a computer, and they don't know what it is. That's how I see physicists looking at your stuff. They're monkeys bashing in your experiments because they don't
But
understand.
you know what? It has to do with a commonality in language that I'll have to bridge to.
Yeah,
Because
yeah,
when I look at some of the physics things, like some of it makes sense, right?
yeah.
And but then there's a half of it that doesn't. So there's a half perfectly clearly states exactly what I'm looking at.
Hmm.
Then the other half says nothing good about what I want to say. So I
Right.
go, well, I cannot say that that's the right thing because I don't see the other part. Where a physicist can explain to me, this is the other part, this is why it's in there, this is the
Yeah.
effect, is it, and it can ask, is it different?
Right.
And I don't know, that would be the language barrier. And then once we get past that, man, because I could build anything. Did you tell me a number on a Tesla coil you want, and I'll hand it to you.
Oh yeah. And it'll work. It'll be tuned perfectly. And that
Yeah.
tuning is the actual gifting because most people can't hit the resonance that perfect that you're showing unless they have super complex circuitry. The fact that you have a resistor and a transistor and that's it, and a fan. I'm telling you what, that
Don't discount that fan, Shawn.
no, no, I will not.
Oh, it's funny.
All right,
Hold
well,
on. I got a question for you.
okay.
Okay. If you were to stack the electrons, would the fields multiply like a magnet?
Um, that's the theory. It'd be more like stacking capacitors, but yeah, well, when you stack magnets, you do increase the magnetism, but I don't think it's exponential. I think it's probably a little bit at the time, at a time. I don't think it's two magnets double magnetism. I might be wrong. I know that the density of the magnetism increases. That means that when you stick them together, they're going to stay together. But I don't know if the actual field um, is stronger with two magnets. I think it's just more dense when you try to pull them away. The fields are denser in between them. But stacking them is electrics is a different thing because when you stack capacitors, um, you are increasing the volume of charge. You're increasing. So if you have a bucket of electrons and then you put another bucket of electrons on top of it, I mean, that's a whole lot of electrons. And electrons means that's a whole lot of electric field density
Mm.
and not magnetism. This is really tricky about, I'm sorry, let me read this real quick for this guy. And then if you were to stack those electrets, would the fields multiply like a magnet? Um, yes, that's my first guess. I don't have two dipole electrets to try yet. I only have monopoles.
Okay.
But Jarvis has helped me a workaround. So I'm going to try stacking them and see. Because yeah, maybe if you stack 10 electrodes, you have such a high voltage, it starts changing the molecular structure around you. I know that AI says if I were to reach my voltages that I want with 1 coulomb of charge, that it would start distorting the space-time around me and the molecular structures of things around me. So that a coulomb's a whole heck of a lot of charge. Now you're probably thinking, well, what the heck is a coulomb? A coulomb is an amp that runs for 1 second. So an amp is a certain number of electrons. So say an amp is 100 electrons. That's 1 amp. Okay, but it's not an amp until it moves. So a coulomb that moves each second is an amp. Or an
Okay.
amp. So if you were to stack buckets of electrons, I think it would be more exponential, logarithmic. I think it would be. I don't think it'd just be doubling. I think it would be a whole lot more.
Hmm. I was just wondering if you could. This is kind of hard because you have to take them out of the wrapper. But once you do, can you stack one and then a little plate of aluminum foil and then another one with the same direction? Would you get a spark if you put the two together from the bottom to the top? Would it create an electrical spark?
That's a really good question. The funny thing about electrets is if you move them, then they create a magnetic field that's 90 degrees of the permanent electric field.
Okay.
That's really bizarre. But if the electret's not moving, then it's only an electric field and not a magnetic field. There's no magnetism. So Jarvis and I are going to play with that property because he thinks that we can find some way to use that to lighten things, reduce mass. So that's an interesting property. Um,
So
what
hold
you're
on, let
describing is
me
sure.
sorry, let me get this right. You're saying if it's an electret and you spin it, it'll become magnetic?
Yeah, it'll as soon as you move it, just turn it with 1 revolution, it creates a magnetic field.
Mm.
It's plastic. And it has nothing connected to it.
Yeah, but it could be disturbing the air and creating heat inside the system that you're not realizing, and it becomes a magnetic value.
This works in space. They've tested it, or in a perfect vacuum or near perfect vacuum. They've tested it where um, when you move an electric field, a magnetic field appears, or if you move a magnetic field, an electric field appears.
Mm.
Yeah, I'm still trying to wrap my head around that physics because it's mind-boggling. I know that Jarvis has a whole bunch of cool ideas about with using these properties because there aren't anything made with these properties. There just aren't. I mean, where are you going to go find an electret?
You
It's
know what I want to see is when he first came on, his little symbol was this round electric, right?
uh-huh.
And that's what I want to see is if you put a tiny sphere in the center, then you put aluminum on the outside and electrify the aluminum, would it then push an electret in 360 degrees straight out? Dude, I've been wanting to see that since I seen him come on the first time and show that, and I figured out what an electret was
Mm-hmm.
because it's great to have it in one direction. I want to see how it works in 360 so we can see if it's more like the dielectric field of Steinmetz.
Yeah, it's that you're talking about a near perfect monopole
Yes.
because it's just all reaching out and it's all the same polarity. It's not a dipole. It's yeah, that's pretty advanced. Jarvis gave me a good idea on how to go in that direction, but I'm still mad scientist mode, trying to figure out, oh, I get a great charge on this, but I can't manufacture it. Or,
Mhm.
oh, I can manufacture this really well and I can't get a charge on it. So I'm in that sort of mode right now. You saw that cracker crumb thing and it had that powerful field, but it was crumbling as I was handling it.
Mm-hmm.
But it had the strongest field. And then you saw those really smooth, clean looking discs, and they had no charge. And I zapped them for hours. So I just kind of want to get to that place where there's a middle ground, and then I want to make the sphere like you're talking about.
Do you
And
think it's a cavity effect?
um,
Because it has cavities in it and it's uneven on the surface that it can get a higher charge?
that's an interesting question. It has more surface area, and you're thinking that the cavities give more surface area, so it's going to have more. I think that's right. Ian's asking a question here. I think that moving charge in the ether pushes on the balloon. As soon as that happens, magnetism forms to equalize the disturbance.
Mm,
That's an interesting way to put it.
that makes a lot of sense.
Yeah, yeah. Thank you, Ian. Ian, are you flying in your helicopter? He'll message me while he's up in the air.
I
All
just
right,
remember
sorry.
that episode of Stargate where he gets in the helicopter and they fly and this thing goes after him everywhere. That's what I see. That's what I see him doing in the air. With
Yeah.
Ian's in there in the helicopter, flying it around everywhere. It's probably just routine flights, but I like to imagine him in an action adventure.
He's he's he does act like a landed, okay. He does act like kind of a superhero because he yawns at how easy it is to fly these giant helicopters, and then he runs to his little lab and it's like he creates all this awesome stuff.
Oh yeah,
Yeah. The fact that he's engaging with his flying in a helicopter, that's crazy.
different level, Shawn. Different
Yeah, he's
level.
on a whole new level. You know that. He's awesome. All right. Sorry, I'm missing you guys in the comments here. See, boss, let's see if you stack the electrets, would the fields multiply? I
That's the
think
one
they
you already
will.
answered. Yeah.
Yeah. What happens if if you smush the coil tighter? That's interesting. You know, Nathan, I think mentioned that earlier with the molding, the injection molding, that I want to incorporate pressure as part of the process. I think you're onto something, John, like Nathan is with the injection molding. Creative Coat says, "Oh, you're kind. I'm not a genius, but thank you." Also, you
Uh,
can use. Say again.
sorry. We got a
No worries.
question right here. Here's an experiment for you. Place it at a fixed distance, but near, not at its peak distance. Then move it back and forth behind it in very small increments.
Let's see if I
Sorry,
can.
I didn't read that well. Go ahead.
Let's see. Place one at a fixed distance near, but not at its peak distance. Then move one back and forth behind it at very small increments. So you're talking about electret on one side of the meter and then the electret on the other side of the meter. Is that what he's saying?
I think he's saying the two to each other, two electrics to each other, and see if it increases. You know, I wonder with that little meter you had, if you sat one right there and then you took the other one out, and
Oh,
like I wonder that myself. That'd just be an interesting,
that's a
little test.
that's a really interesting test. I'm taking notes because that is really interesting. Thanks for the concept. Just writing it down here. Yeah, so stacking them, is the field going to expand more?
I wonder
And
if you're going to pick up a charge value.
that's a way to test stacking them right away, is just stick them together and see what they do next to the field meter.
Hmm.
Let's see here. Oh, no, let's see. Yeah, Neg Rest says blue requires a higher frequency. I think we talked about that, how that blue light came from the compressing, making the signal, the wave smaller or tighter.
So if you have a higher frequency coil, is what he's saying, that then you can get the blue color?
Right.
Well, that's that. I got a 1 megahertz Tesla coil, and
Yep.
then 250, 270, I think, kilohertz on the other one. So yeah, let's do that.
You have it all set up. You just wrap the wire around from 1 megahertz Tesla coil and then off the kilohertz one, and you should see the lights. That sounds really cool.
By the way, I just want to say this so everybody understands. Shawn and I built this coil. So I came to him. He said he can get a Tesla coil working, and I was frying everything in the world. And he said, no, I got you, Nathan. We'll do this, right? Then we looked at, once we got past that, we want the ZVS to work. What's a perfect coil for it? And because of Shawn getting in there with the YouTube Tesla coil, or sorry, not YouTube, with the Tesla coil Java, he was able to program that thing where I could get the perfect number every time. So now Java TC, we go through there, man, and we built this perfect coil, and every time I put it in there, it's perfect. It doesn't change, Shawn, no matter what I do. You get a perfect resonance out of this thing. The coils, the amount that's there, the amount of the windings on the number 2, every single part of it. So I just want to make sure everybody knows this. I didn't build that on my own. That's Shawn and I working together and getting it worked out. And everybody's working on it, man. It's amazing to see how many people are liking it.
You made it accessible, and don't sell yourself short. You helped me a ton. I remember printing out the Java TC, and I'd be focused on one thing, and then you would look down on the stats and go, oh, it's right here, and I go, where is it? And so it was a team effort. Java TC, though, was not easy to work with, and but we figured it out somewhat. And you're right, it comes out perfect every time. That's awesome. Yeah, that was the genesis of our learning. Now you're the one that mastered the Slayer circuit. So, and the thing about a Slayer is that since you've been able to make it more high power and indestructible, it tunes better to the resonance than the ZVS or really any other driver I've seen. I mean, I think there's the DRRSTC, the dual resonance solid state Tesla coil. I think that has a feedback, but we're talking 1,000 components, and we're talking about, yeah, it's not one transistor like yours. So yeah, no, I brag about your Slayer all the time.
Well, when you can pull a 5-foot field out of that Tesla coil I got, man, that's impressive.
So impressive.
When you can run 40 volts and it doesn't blow up on you in the first 10 seconds, like that, to most people that just started out, man, it's a game changer, because now you can do all the experiments in the world you want. That's what made it accessible, is that circuit and the ZVS. Once we dialed it in, man, doing experiments one after the other, your stuff doesn't blow up, it doesn't heat up, it's perfect. Yeah, amazing. I wanted to answer this real quick. Michael Perron asked that vortex, that was just the number 2 wire that comes off the Tesla coil, and it puts off ion. So it's just going to get an ion propulsion in one direction. That's all that it's doing. And it's just creating that swirling vortex, and it looks like it comes out at different levels. It's one of those awesome effects that you just see when you're building this stuff, and you go, man, everybody's got to see this.
Yeah. Good response. Good question. Longtime fan. Oh, thank you, Michael. Michael or Michelle?
Michael.
The strongest Electret that I've ever made was when I turned on the HVBC. I had to leave the house, and the HDPE cooled, and that's polyethylene. He's saying it's high density polyethylene HDPE, cooled with high voltage off. Apparently, the plate still held a strong charge.
Really?
Yeah, that sounds awesome. Great job, Neil. I it's interesting that you keep the plates and you didn't charge it while it cooled.
Mm.
Yeah, that's interesting. I was putting a little kink in my head, but no. And you had to leave the house, so definitely you were electrifying the house. I'd be interested in what high voltage source you have that would cause you to leave the house.
Oh yeah, we got to hear that story.
Yeah, I'd be interested in that power supply.
Yeah.
Because I'm going next level in the next week or two. You guys won't believe how I'm gonna go next level with power next 2 weeks. So I'm just getting you a little taste. So Coat says, Shawn, do you see amplification when running high voltage, high frequency DC when earth grounding? Okay, so here's a 30 kilovolts DC. So what's the current? What's your current on your power supply? I'll tell you how dangerous it is.
Hmm.
So when I'm grounding, I didn't show that in my presentation. One of the ways I clear my workbenches, I have a wire that's connected to my house ground, that's connected to earth ground. And so whenever I do any measurements, I grab that wire and all my body charge disappears to zero. And then I do my measurements.
Really?
Is there an amplification when I connect to the earth ground while I'm charging? I've been connecting my high voltage generators to earth ground every time. It seems like it's more. It seems like it's stronger. I couldn't tell you for sure, but if you connect the negative to ground, it seems like it's stronger. It seems like. What do you think, Nathan? Do you think it's amplified when I connect the negative side of the power supply to ground?
There's definitely energy coming from the ground, depending on how you set it up.
Yeah.
So either it goes two ways. If you set it up in one way, it's discharging the extra energy to the ground. If you set it up in the other with the negative field, it's pulling that energy to it, like we saw in your Tesla coil, right?
Yeah.
So it really depends on how you set it up and what you're looking for. You're in a conventional setup where you're just running high voltage, so it would discharge the energy to the ground and get rid of it. So
Well,
that
actually, I'm just connecting positive to one side of the electret and negative to the other side, and that's how the power supply works.
oh, hold on. So
And
you're
then
just
I'm
in
just
like
grounding. I'm connecting the negative to ground also. Now
like
it's still going through the electret,
a
but the
DC
ground is
flyback
from
loop.
what's that?
It's a DC flyback loop. It's just positive out, goes back into the negative on the bottom. Right?
Correct.
But there's
And
no negative to grounding to the wall or to the outside and the spike in the ground, nothing like that.
okay, so the circuit only has the positive and negative. It doesn't need grounding. That's how it works.
Yes.
I
So
have tested it just negative, positive, plastic in the middle, and I have an electret. Let's say it's 100 volts. But if I connect the negative and positive, put the electret in between again, and then run the one negative side to ground, the electret has more charge. I don't know how much. I don't know if it's amplification. Um, well, it's increasing, so I guess you can say amplified. Does that make sense?
no, it does. So you might have to take a look at your circuit again.
Yeah, because it's not really intuitive. If you just have negative and positive, let's say you have a battery and you hook it up to your car. No, that's not a good example. Because the battery is connected to ground, the car is ground. Let's see here.
Michael Perone had a comment on what was going on. It was very interesting to see what he had to say.
Okay.
So we wanted to pop on for a minute, if that's okay.
Yeah.
I know you're getting close to your time.
Yeah. I might have to go a little early today. I mean, I'm having a blast. I don't want to go, but Not 100%. But yeah, it'd be awesome. Is he going to join?
We'll see in the next few minutes if he sets up real quick.
Okay.
It's always interesting because you have. I always see an Electret as a TC flyback, right? And you thin it down, you raise the frequency, and you get it real thinned out like a static. And then you send it through. You have to have enough magnetic value that it doesn't go everywhere. So
Okay.
it's directed static is the way that I see it.
Yeah.
And that's when I see it's just a loop. It's like a
It is a loop.
it's a DC loop that sits in there. So to ground that out wouldn't make a lot of sense to me.
So,
Hey, what's going on, man?
hey,
Hey, yeah, good to finally join you guys for one of these streams. So I guess I'll be quick because it sounds like Shawn had to go. But I was recently doing some experiments, and I came across a very interesting effect. And I
Okay.
think it fully explains why a lot of these power things are attached to ground. So so I was playing basically with the Manella circuit, Arthur Manellas's device, if you guys recall. So that's supposed to run at like 180 volts or something like that. And we were trying to search for false positives. We were looking at maybe the billet had a magnetostrictive effect and was vibrating, and maybe that was causing like thermoacoustic effect, which looks like the thing cools down instead of actually like having a cold electricity effect. So we were looking at that, and the other thing we were looking at is like, is it possible that the temperature sensor was like grounded to a live wire or something, and that was messing with the temperature reading? So the theory behind this that I initially thought was okay, if he's using a thermistor, it should be the same. It shouldn't change the temperature reading. But if he's using a thermocouple, it should change the temperature reading, because I reasoned that you could think of different metals as having an ideal gas of electrons inside them that has a different compressibility. So when I actually tested it, what I found, interestingly enough, is that the thermocouples, even shorted to high voltage, with a differential probe measuring the temperature difference, the thermocouples actually were very consistent with the temperature reading. And actually, the RTD actually changed a lot more. Not the RTD, the thermistor. So that was surprising to me. But in hindsight, it makes sense, because the thermistor has a metal oxide film, semiconducting or just poor conducting metal oxide film. And that metal oxide film, the amount of charge carriers in that will depend on the voltage. So actually, at high voltages at high voltages, the metal oxide film should actually change resistivity. In hindsight, that should make sense, because it's the same mechanism as when you're gating a transistor, sort of, just without another pole, or the rest of the world is the other pole of the transistor, or the I don't know the correct terminology of these things. Sometimes I'm more of a physics guy, not an electrical engineer. But you get what I mean. But so anyway, so that was interesting to see. But also, what that means is that the compressibility of the ideal gas of electrons in these metals is actually quite small. And so when you're pulling electricity from ground, when you're pulling power from ground, what you're really doing is you're making a larger reservoir of charge to pull from, so that small compressibility will matter more.
Yeah.
So it's like you have your coil that's shuffling charge back and forth, and you put a ground somewhere along that, and it's like the Venturi effect with a gas.
I was going to say that.
Yeah, and the Venturi effect, it will pull in, it will create a pressure differential and pull in charge from the ground
From the
wire or
earth,
push
from
it
the
out.
earth. Mhm.
Yeah, or actually no, actually it would generally will pull either direction it's flowing. But yeah, that's the basic concept is like you can only
Yeah,
pull in, you can only pull in charge into your circuit if the thing is well grounded, because you need a large reservoir to draw from.
right. Yeah. No, perfectly said. I didn't quite remember the actual name of the Venturi effect, but I was gonna try to explain that. So I think you're spot on with that theory. Yeah, I think it makes sense. And it makes sense because in my testing, I have stronger electrets if I ground one side. Yeah, no, good explanation. Thank you.
Cool.
Awesome.
Yeah, hopefully that'll help people's research and experimentation. One other thing about that though is now we have an absolute voltage sensor, not a relative voltage sensor, because we can take a thermistor and a thermocouple, and we can compare the temperature differences or the temperature readings of the two in order to see what, or at least the voltage drops across them with a differential probe, of course. But basically, they won't agree at high voltage. So now you have a way of determining if there are literally excess electrons or holes on the material. At least voltage in that sense you have. I mean, global voltage through the whole universe, that's another question. But at the very least, you can tell how much excess charge you have on a thing.
Well, there you go. That
Very
helps.
useful piece of equipment, potentially.
Yeah, yeah.
Yeah, because you could throw off your whole experiment.
Yeah, that's a whole. Give that a try. Yeah, I mean, get some thermistors. They should be metal oxide thermistors, and get some thermocouples. Type K is what I used, just the standard thing, and give it a shot, and you'll see the temperature readings disagree at high voltage. So voltage is the more fundamental thing in physics, not the electric field, sort of, or at least that it's a. I mean, we already know from the Aronoff-Bohm effect that magnetic vector potential is a physical thing with physical effects associated with it. Now, absolute voltage, or I guess voltage in a sense. Well, I don't know. I don't know exactly how to map this new voltage concept with the excess charges
Can you
to
define
the relative
absolute
voltage
voltage?
concept, but I think it's fine as a yeah.
Can you define absolute voltage?
What I mean is whether you, I mean, so you can have the whole voltage relative to the environment. What I mean is, do you have excess do you have excess charge monopoles on the thing? Like either electrons or holes.
Okay.
So there's some, like with a transistor, when it's off, there's some steady state distribution of charges in the thing, and you'll have some deviation of that due to the extinction region of semiconducting structures. But then if you stick a whole bunch of electrostatic charges in there, it's going to change its resistivity.
You can turn those transistors on and off.
Yeah. So the
If you
physics
take
is
a charge
different.
field
You
next
have,
to it,
yeah, if you just have extra charges on, and in fact, I think back in around 2014 or so, I recall a guy with some interesting. Well, I don't know if he ever mentioned he was doing secret stuff or anything like that, but he was working for private companies and things, and then he went back into private industry. But for a little while, he was a adjunct professor at WPI or something, or an assistant professor. I don't know what the situation was. But he was at WPI for a short time, and then he went back to industry. And his whole thing was superconductors, optically pumped superconductors. So you hit something with a laser, and it becomes superconducting. And he mentioned something about molybdenum disulfide doing this with either green or infrared light, I forget. But the other thing is it has to also have an excess electrostatic charge on it. So there's a few papers I was able to find after that, but most have been scrubbed from the web as far as I can tell. But there are a few papers I found where they actually use like the amount of excess charge stuck on a chunk of superconductor to modify the Fermi, what was it? Not the Fermi energies. Yeah. So that the band structure of the material in any case. And then that
So-
modification of the band structure in some cases would induce superconductivity when you have the electrostatic charge present. And sometimes cold temperatures, sometimes with driving it with a laser. Anyway, that's all I wanted to.
So I'm sorry, absolute voltage? What, I'm sorry. What is absolute voltage?
So absolute voltage would be a measure of how much excess charge is packed onto the material. So basically,
You're saying that you're saying include the charge of something, the electrostatic charge of something, and include that from the electric charge from the components in the circuit.
yeah. So in some sense, yeah, a material without any excess charges on it is at 0 voltage, sort of.
So hold on.
With
If I
respect to
understand
physical properties and phase and quantum phase transitions and things.
the material is just a baseline. When you add something to that material on top of it, it sets out a higher number. Is that what you're talking about? A total amount of everything together?
Yeah, so there's this relative concept of voltage, and you can have an uncharged object next to another thing that's at high voltage. And so relative to the other thing, it's not at, I mean, it's in the high voltage area, but it itself doesn't have excess charges stuck to it.
We see something, and I don't know if I'm way off base here, but in Shawn's Tesla coil, where he can take a spool of wire and sit it next to his Tesla coil and use it as a ground and just bring it next to the Tesla coil. And instead of it going this way towards it and to like ground it, it's actually pulling electrons off of it and shooting amperage in there with his high voltage coming from that wire itself, not grounded, just a spool of wire, nothing but the air around it that's there. And it forces itself to that Tesla coil because the Tesla coil is pumping. So as it oscillates, it's oscillating that energy in regardless of the resonance value.
Interesting. I'll have to take a look at that sometime.
Yeah, I was experimenting with I got some 3-inch copper spheres. I use those as ground. I have rolls of 12 gauge wire, magnet wire. I use that as a ground. I live in a 123-year-old house. So there's copper everywhere, and I have like 10 ground stakes. And so this house is really well grounded. So it's been really interesting to see the differences of how they react as ground. So absolute, I just need to go back to this because I think you explained it well. I just don't think my brain is big enough to understand fully. When you say absolute voltage, you're sort of saying that you're considering all the charge in the equation. You're not just going by voltage drop across a resistor. You're literally saying, no.
Voltage is typically defined as a relative measurement. I guess if you want, you could say we're measuring how much excess electrostatic charge is on a thing. You could say it that way if you want. But ultimately, you can derive voltage from that by considering the environment of the thing. So if you take all of the excess charges measured on all of the objects, you can make a map of what the voltage should be from that. So in some sense, it's equivalent.
Well, oxidation.
Fascinating.
Sorry, I can't even say the word right. When it oxidizes on a piece of aluminum, it changes the value of the energy in that aluminum. It'll send spikes through your system. Anytime that you pull any kind of burn spot, anything, it's a dead spot. So what it does is it can't calculate the amount of amperage or the voltage going through it properly. So it sends different signals throughout your system. You may just see it as a dirty spark gap, but when you break it down, it's a hindrance. You know what I mean? It becomes a diode, just like in a old AM radio or a trench radio, something like that. It changes the value inside of it. So you have to watch any coding that builds up on anything because it'll throw off your experiments and start putting spikes in places you didn't expect. Like all of a sudden you get this huge amperage spike, blow your
Yeah.
system, and you didn't know why because it ran perfectly. Well, you had corrosion or something on it, and boom, completely gone. And you get that with inconsistent metals. When they press out the metal and there's peaks and valleys in the metal, you get the same thing. Or if you use a high voltage spark gap with this kind of stuff, and as it jumps around, it's calculating the value of your voltage and amp leads different. So
Yeah. I mean, you get your oxidized razor blade to turn it into a nonlinear device that demodulates radio signals if you were
Oh,
to
cool.
use it as a diode,
mhm.
because the oxide works together with the material and it can create a diode. I mean, a rudimentary diode. But yeah, I mean, when I saw, have you seen this experiment? I'm sorry, your name again?
Michael.
Michael, sorry, I'm terrible with names.
No worries.
Yeah, so have you seen some of Nathan's experiments?
A few. I've been.
Oh no, we lost them.
They freeze them out on that.
I shouldn't ask that question.
Oh,
So,
that's
Hey,
funny.
sorry about that. I froze a sec. I think um, I'm trying out the what's that? The Starlink satellite stuff, and the only spot I can put my antenna is like kind of close to the house, so there's a blind spot at the edge of it. So
oh,
occasionally it'll cut out. Yeah,
Starlink is awesome. I love it.
yeah. This one's the version I can take hiking, so I'm gonna.
Nice. We're gonna order that movable one because it's a long drive to our cottage up north, and so we can take it with us in the car. We can put it on the deck at our little house and have the Wi-Fi, the download and upload speeds. They smoke. I live near Chicago. They should have a good infrastructure. No, it's Starlink is always faster. It's
Yeah,
always better. In fact, the upload and download speeds are so quick, you think your computer's broken because you'll click on something and you won't even see it load. And you go, did I click? You'll click on something else and you go, wait a minute. Because
yeah,
we're so used to little kind of lags because you're kind of in the zone. Nope, not with Starlink.
yeah. I've been impressed with it so far. I just need to find a better spot to put the antenna so it's got a better.
Yeah.
But yeah, that's. I should probably head out. Been nice talking to you guys. Yeah,
Yeah,
Shawn,
thank you for
I'm
that.
looking for multi-megahertz, higher frequency Tesla coils. It sounds like you got the skills to build them. We should chat more.
Yeah.
An interesting project for that.
Are you looking at bipolar or just standard Tesla coils?
High frequency.
I don't want to give away any surprises, but we're gonna just open source it all at once we have it done.
Oh, okay. Well, that's fair.
Nice.
Yeah, maybe you guys could mirror the live stream or something when it's going on.
Yeah, that'd be awesome.
Yeah. Awesome.
Mm-hmm.
Yeah,
Hey,
absolutely.
nice meeting you.
Yeah. Nice meeting you too.
Right on, Michael, man. We'll see you in a bit. I look forward to the open source when we're all done.
Yeah.
See ya.
I'll have, since you're connected to Nathan, can I just send him, can we connect on Facebook Messenger maybe?
Oh, I don't use Facebook. I only use Signal these days.
Oh, Signal?
Yep.
Oh boy.
I mean, I have emails too.
If I was going to say, can Nathan give you my email and then we can connect?
That's fine. Yeah.
And then we'll figure out Signal.
Sure. Sounds
Okay, I
good.
appreciate that.
Cool.
Right on,
Awesome.
Michael. Thank you for coming on. I appreciate it.
Okay. Yeah.
Yeah.
Perfect.
And yeah, see you guys around.
Okay. Take care. All right. So in the comments, always great discussions. Let's see. They're talking about 150 to 200 miles per hour. Boy, this is a deep conversation.
Well, the chat's super smart. I mean, I know
Yeah.
a lot.
So Deadfish says the president of the U.S. shot down 3 UFOs 30 days later.
Well, that's interesting.
Coat is he's quite a celebrity. Everybody's saying hi to him.
Hey, he's awesome, Brendan.
Yeah, that song. His song is so clever.
Yes, very good at that.
Yeah, he's very good. He plays the drums.
Yeah.
He's really
Oh, yeah.
good. I thought I would have never guessed he was a beginner. He's gifted. So 8th Center has an experiment for me. Shawn, here's an experiment for you. Place one at a fixed distance near, but not at its peak distance. Then move one back and forth behind it. Didn't I already read this?
Yes, we went over this one. Sorry.
Sorry. Yeah, I'll try stacking them how you're saying 8th Center, and we'll see what happens. Right. Got about 10 more minutes.
Resonance equals drums. I love it. Huh.
It's kind of true. The drums are given the resonant sound, right? Darren asks, Shawn, could you use electrets to sustain an static field, a bubble inside an induced harmonic to repel the vacuum? Let's see here. Sustain a static field inside. What's an induced harmonic?
I would imagine he's got another field on the outside of some sort, and he doesn't specify which one.
Yeah,
But
harmonic. Yeah. Harmonic has the idea of frequency or vibrations, sound. It's a resonant or harmonic. To repel the vacuum. Oh, so maybe he's thinking there's some interaction between a high static field and an induced harmonic, so that then you're in a bubble in space because the space is a vacuum. And
Well,
so maybe that's a way to create a shield when you're in outer space, in the perfect vacuum of space.
I think the question's close, but it has to do with which field you're in. You can hold back a static field in the open air. There's no question about it. You have to build a radiant field around it from the inside of your Tesla coil. I'll tell you that all day long. I can push them across the lab if I switch the sides of it, and I can force it everywhere I want to, or I can hold it in. That's not a problem. If you want to build something more out of that, where the two sides as they're interacting like that, and you want it to come plasma, in order to create a massive field inside to create an EVO in open air, that's difficult. It's easy when it's in compression. So if you took what's the material you put around everything? If you took that and you put that's your compression, right? And I wanted to create a charge in the end of a wire on your coil. Well, then you can create an EVO inside that all day long, and it'll start tearing through the entire thing. That's not a problem. You can do that. It's just about charge compression of the electrostatic field at that point. Then yes, it would be 100% correct. There's not much of a difference between that and taking mineral oil and basically having a bubble in there, because everything from the mineral oil goes slow through it. But when it comes through, it's almost a pure electric value that goes in there. So it becomes static inside there in nature. And as soon as it hits something, it converts over to an amperage field and just fries everything around it. Creates pure heat. You know what I mean? That's why it starts doing that. That's why you suck all the air bubbles out of everything, because you're going to get these little fry daddies that come by and ruin your wire.
Yeah,
So,
no, that makes sense. Wow, that's deep.
Yeah, not much difference in all this. You just have to know which components to put together to create it.
Yeah, yeah. And how would that relate to what you just described if you were in the vacuum of space?
This vacuum of space is no different. It's just an energy field out there. You still have to create both fields. You can't get around that.
Makes
You're
sense.
you're never going to get anywhere close to this unless you do. It's so simple, two fields. If
Wow.
you can create a radiant field, you could put a static field inside of it all day. And
Yeah.
not a problem. You have to ionize the air as well, just so you know.
So you've mentioned this before. You know, we have the magnetic field and we have the electric field. But you're saying there's a third field, and you call that the
I call it
scalar
radiant field.
radiant
Like,
field.
here's the thing: if you take a Tesla coil and I set it right here, if I put one spike going out, I see what you see on the screen behind our pictures, which is basically a breakout that looks like that, and there's little lines that break out into it. But if I put it into a sphere, what happens? It builds out in a radiant field. And it basically takes all your values and puts them down based on the temperature and distance of the area in the room. That's it.
That's
Now,
a huge factor.
yeah, so you have this sphere. I put another Tesla coil over here as a receiver. There's a null zone right in the center. No energy whatsoever, no light bulbs
wow.
lighting up, nothing. But both of them themselves have energy. So your primary driver has energy, your secondary coil with nothing attached, no ground, nothing, just a number 2 coil with the sphere on the top. When it's in resonance value with this one, absolutely perfect scalar field from one to the next with the null zone in the center, just like the planets show. And it has to do with the geometry of it. You literally
Yeah.
change the geometry to get your field to work that way. A lot of people just think it's a single geometry, the single breakout. You know what I mean? You have a breakout on both sides. It's not. It's you have to have the spheres in order to get that field to break out the way you want it to. So
Yeah.
it's
Yeah.
it's just a building difference.
When you have a sphere and no sharp edges, we're talking there's a lot that increases the voltage, that increases the pressure. I mean, it makes total sense that you're building that pressure up on the sphere, because spheres don't like to discharge. Spheres like to hold on as much as they can because it's equal on all sides. There's not a sharp edge, there's not a corner. And but that idea to have two spheres, one Tesla coil plugged into power, the other one just at the same resonant frequency, that's profound. I'd love to see that. I think that's going to be huge. Now you've done
Well,
it with the coils, but with the spheres,
the sphere, all that is a calculation of the value of the number 2 coil. That's all you have to do is what's the top load? Now I need to calculate it to my coil and see what the actual frequency of the entire device is. Once that's a known, I can now make a driving coil to that exact frequency and do it.
right? Yeah,
Or if I start with the other one and make a driving coil, I can make this one exact. It's a little harder with the top load, so you always want to start with the second one and then drive a number to it. You know what I mean?
interesting.
Yeah, so that's a little different. If you don't have a top load, it's easy. Then just run your primary driver and build one to the exact oscillating
right.
frequency, and you're good to go. It's a little bit of difference in building, but you get the idea. It makes it easier one way versus the other.
Yeah,
I think people are going to trip out if you put that rod down the center of it like we do, and we create a radiant field. And I'm going to tell you it's radiant because you can take your Geiger counter and do this test. Go over there and compress it in a pipe with mineral oil around it. The field can very slowly get to the mineral oil. I mean, very slowly. So that amount sits in there and builds up like a volume of gas. So as it builds up, it pushes the field in and then breaks it out even bigger. That amount of energy is the same thing Edwin Gray used in his device in order to get all the amperage field. Because if you take high voltage to that field that's in there, you have a mass amount of energy, and now you convert that mass amount of energy to an amperage field in an instant by putting high voltage on one of the rings on the inside, like Edwin Gray did, and
yeah,
boom, instant amperage. But as soon as you let off the high voltage, back to the radiant field, and it's held in, so you're safe. So then, boom, you switch it again. I showed this field flip switch in a bipolar Tesla coil versus my regular Tesla coil. I
yeah,
flip it all day long and get
yeah.
amperage field, then go back to a radiant field, back and forth, back and forth. None of them have static coming out. There's no static value, and that's why it's radiant, because it's the longitudinal versus the transverse and oscillation that creates the radiant versus a simple. This is what the numbers say, so it has to be static. Well, there's no static. You've worked with Tesla coils for a long time, where it's a static electricity.
I haven't seen static electricity on my Tesla coils. I mean, Yeah, I don't know. I'm trying to just digest everything you said. The it's a lot. You're a pro. I'm just thinking when you say current field, amperage field, that's the emphasis on that one is magnetism because or magnetic field because uh, coils are made to control amps or current.
Mhm.
And how it controls it is through magnetism. If you try to rush current in too fast, the magnetic field gets big and slows the current down. If the current tries to go weak, then the magnetic field will go bigger to match the what's missing. And so that sort of coil working as a current device supplies current, gets rid of current, supplies current, and slows current, fast current. Um, is that what you're talking about? Is that same action as a current field? I
Well, the
don't know if
current
I'm
field
asking that right.
in a Tesla coil, it's basically your number one coil. So it's the transverse field. It's the magnetic value. Okay, just like this. And
Yes,
in that, it induces into the secondary device, right? So
correct.
then it goes through and it wraps and it hits in every level, and then it should come out static. Everything in every book tells you should be static. It's an air core transformer. You're converting to electricity, right? Static is generally electricity when in open air. The
Okay.
problem is it doesn't do that. If you're in DC, you get barely any breakout. And if you have zero breakout, it just in a field.
Mm,
And it's a
yeah.
monster field. The second you get breakout, right on down. And you'll find it when you go 5 feet with a light bulb. You'll find that that's when the breakout starts to happen. And as soon as it does, the distance on that will go no further. You
Mm,
you stop the distance in it. So you have to change the value of it to bring down the amount of energy in the Tesla coil, right? So this is where the amperage part takes a turn. If I have 15 volts, I broke the field and it's no longer resonant. I just
mhm,
lost about 1 to 2/3 of my energy sometimes. Okay, right there. Boom, dropped in a different resonance value. It was resonating at 150 kilohertz, dropped down, and now it's resonating at 347 kilohertz, right? Not a
mhm,
bad signal, but it isn't the right one. So now
mhm,
I drop it down to 10.1 volts. As soon as I do that, my amps just dropped as well. So I'm getting barely 2 amps in a field, right?
mhm,
That's a hard sell in order to make that thing run. But then you start to realize it's not the amps and the volts. It is a frequency carrier. I am triggering the frequency in it. As I trigger the frequency in it, I'm asking the field around me that's radiant, please bring in more energy. What happens is your field size starts doubling on you. You can start pushing this thing 6 feet, 7 feet away with another coil, as long as it's at the correct resonance value, and boom, instantly it turns on. There's no
mhm,
question. But you go, well, I want all this amperage in my testicle. And in AC, it makes sense. In DC, it doesn't. It's a
mhm,
frequency coupling between the longitudinal and transverse that gives you that amount. That's why it's a different field.
mhm,
Because you're pushing this thing, Shawn, literally across the room. Like when I say everything's RF hot, I mean you can't go over your printer and touch it. You can't go over here and touch it. Everything. I can't even touch the power source. I broke 2 power sources this week just putting it in RF hot, and it fried 2 power sources because I'm within 5 feet of it. I mean, think
yeah.
about that. I'm 5 feet away with a power source, and it's fried. There's too
And you'll
much
burn you,
energy.
right? It'll burn you
Oh,
if you touch it
it'll burn
anywhere.
you. It starts to melt solder. It it
Yeah,
it's
it's hot.
it's yeah, it gets bad. But that's what I'm trying to
Interesting.
say. It's a lower, all of it lowers. And this is the confusing thing to people. Why in the world are you putting less energy and getting more energy out? They can't understand it. And it's because I don't want to use your man made energy when there's energy in my room that I could pull for free. That's what it is. I'm creating a resonance to draw in the amount of energy that I want from the room.
Mhm,
It's dude, it's a total mind blast when you look at it and look at physics and go, I want a room temperature superconductor. Well, That's the only way you're going to get it.
Hmm.
Is you have to understand how resonance works, and then you could pull higher amounts of energy based on your resonance value. Because it literally on your oscilloscope, say you got something like this, right, which you say is probably a pretty good signal. Now, when it brings off like this on your oscilloscopes and goes off the chart, you just doubled or tripled your signal and put
Right.
it in the correct oscillation, and it took off. And
Yeah, it's a magnification because of stacking.
Mhm.
Yeah. Wow, that's a lot. A lot of good
Sorry,
stuff.
don't mean
That's
to
a
chew
lot of
your
good
ear.
stuff.
It is a lot, but it took probably, I don't know, like three to 600 tests to figure all of it out.
Yeah.
And then now to sit there and be able to turn it on at will and flip fields and everything else, it takes a lot of work.
Amazing. Yeah, it's amazing. When you said all I'm really interested is just resonance. I was talking to Jarvis and we both said, yeah, we're all about resonance. Like there's just something special about resonance and resonant frequency, because everything's vibrating, everything's moving. But when you reach resonance in any material or electricity or vibration, it has this exponential effect, and it creates all different kinds of new phenomenon, and it opens up doors to all kinds of energy, because that's what you're doing in the end. When you learn to master resonance, you're extracting energy everywhere, or you're maximizing the energy that is available, and it's more than people think it is.
Well, that's why
And
it's so important. We took that rodent coil and saturated it with energy, and it takes about 30 seconds to a minute to dissipate.
Mhm.
That it tells you we're dealing with the environment in the room now, because I took a negative rated energy field, which means I have almost no losses whatsoever in that rodent coil. There's no heat, but then it's getting colder as it sits in the room. It's
Yeah,
starting to have that effect of cooling down, cooling down, cooling down. What happened? Well, when you don't have heat, you don't have loss. So then the field bounces around in resonance in there longer. And that's why it stays longer, because the resonance field doesn't go away right away. It continues to bounce off of each other,
yeah,
and then eventually it dies out, right?
right.
Because you still got to have a push to it. So that's how I knew right away, Shawn, that we cannot put hot energy into coils and get any kind of over unity. It just won't work.
Mhm.
It's too much loss. You lose so much immediately. I mean,
Well,
Jewel
yeah,
Thief's
you lose
closest to
energy.
it. Yeah, Jewel Thief's closest to it, but what is it? It's really a buildup of energy because you didn't turn off the energy. I think people forget that. You did not turn off that energy. You didn't give it a value and then that's it. You continuously gave it a value. So you think
Mhm.
it hit over unity, but it
Mhm.
didn't. So when you go to loop it, it fails because you're thinking in a single value. It's
Mhm.
thinking in continuous value.
Yeah.
Now, when you go to loop it, it fails. And that's 99% of the problems I see out there when we have a non loop system claiming over unity. You just shouldn't do it because it's a misunderstanding of a reading of a gauge
Mm.
that's giving you that. It's giving you a snapshot versus the total picture of the entire thing. My
Right.
opinion.
Yeah, good stuff.
Getting towards that time, Shawn.
Yeah, I'm trying to take it in, but
Oh, it's a
it's
lot. It's like a
so
fire hose I'm shooting at you.
yeah, exactly. No, it's so good. And I got some good notes. I appreciate you having me on, Nathan, and much love to you guys in the chat. You guys are awesome. Sorry if I didn't get to your questions. I hope to see you guys next Wednesday. And Nathan, thank you so much.
Right on, man. Thank you very much for coming on, Shawn, especially with the Electrits, man. Nobody's doing it. So you're like the total insight to the world of what's going on there.
Oh, I
And
appreciate that.
just a little side note, I love the easy bake oven stuff, man. It, it it's like somebody had like a yard sale next to you, and you're like, no, I think I'll take that and all the easy bake stuff. No, I know you buy it separately. I'm just joking with you, but
No,
it's fun to think
it's
about in that way.
Yeah, no, it's totally like that though. It's totally junk. It's funny because I'll buy stuff at the thrift store and they're saying, "Oh, do you want to plug that in and see if it works?" No, I just need a capacitor. And they're like, "What?" Yeah,
He goes,
that's-
so you don't understand the reference. He takes stereo. What is it? Those things, not a capacitor, but the heat sinks,
yeah,
and he
yeah,
makes capacitors out of them. It's
yeah,
hilarious because they fit into
yeah,
each other like this, and you adjust the capacitance based on
yeah.
the distance. Dude, people still haven't figured that one out, Shawn. That's so amazing.
Thank you. I appreciate it. You guys are amazing. You're amazing, Nathan. So I'll talk to you soon.
Right on, Shawn. Thank you very
Okay.
much. Hey,
All
everybody in
right.
the chat, thank you, man, and have a great day. And if you guys can, help out Joe Go Mining, man. I want to see him out there again, especially since we're losing all this weight. John, I'm doing good, man. People are going to be surprised, and I think they're going to be surprised with Joe as well. So look
Nice.
forward to that. And then we're going to be eating some wings after that, Shawn. And they
Okay.
promised to burn my face off. So we get to laugh a whole lot.
Okay. All
All right,
right.
guys,
Talk
that
to you soon.
said, have a nice night, man. Thank
Hey,
you.
good night, guys. Bye.
The old man built. The old man built. The old man builds is broken in the head. People not seeing reality has put him in the red. Where conscious and spirituality been stricken from the norm and replaced with the ignorance of basic magnetic form. The geometry of God keeps running through his head. That's what makes old man builds broken in the head. The old man builds. The old man builds. Spheres of destiny are spinning in his mind, making him travel back and forth in time, battling the establishment for just a little recognition. Has him forcing the world to understand his premonition. That world will have all the technology in the end, even if it means his life will fail to extend. The old man builds. The old man builds. The old man builds. The old man builds. Fears of destiny are spinning in his mind, making him travel back and forth in time, battling the establishment for just a little recognition. Has him forcing the world to understand his premonition. That world will have all the technology in the end, even if it means his life will fail to extend. The old man builds. The old man builds. The old man builds. The old man builds. Fears of destiny are spinning in his mind, making him travel back and forth in time, battling the establishment for just a little recognition. Has him forcing the world to understand his premonition. That world will have all the technology in the end, even if it means his life will fail to extend. The old man builds.